right, welcome back. We're going to press on and get out of the rabbit holes that we have dug ourselves into, the pleasant and happy rabbit holes of studying plane waves and partial wave expansions. And you may remember that the particular rabbit hole we're in now is an attempt to take ownership of this asymptotic form of our spherical Hankel function. And the goal there is, if we understand this asymptotic form, we will understand the asymptotic form of the spherical Bessel and spherical Neumann functions, which are really important for understanding scattering theory. And the way we were getting to this process of understanding this asymptotic expansion is to use a method of steepest descents, which required an integral representation of the Hankel function. And in our last lesson, we brokered our understanding of the integral representation of the gamma function, and we ultimately landed at this integral representation of the regular Bessel function. Remember, our goal ultimately is the spherical Bessel function, right? But we're using these definitions where the spherical definition is defined in terms, the spherical Bessel function is defined in terms of the ordinary Bessel function. And by using this definition of the ordinary Bessel function, this integral representation, we're actually exploiting these integral representations that you may have learned when you studied these functions for the first time, if you did in a differential equations class, for example, or a mathematical methods class. So now we brokered that into these two definitions of the Hankel function. Now you'll notice there's actually a 1/2 missing here, right? In other words, if you connect these two contours together with this definition, you end up with something that is twice as big as the Bessel function. So ultimately, we need it to be, but it's always a constant factor, right? And all these solutions to differential equations are only are arbitrary to a constant factor. So this constant factor was sort of pulled out during this process, but in the end, you do have the required relationship, right? The ordinary Bessel function is the sum of the two Hankel functions divided by 2, which is why this factor was pulled out, right? This arbitrary constant factor. So it's all part of the definition. It's all built into the definition. But the point is this guy right here. This is the Hankel function of the first kind, and it's exactly in the form that we need. You may remember that in order to execute the steepest descent, we needed an integral form that was a complex integral. So here we have the complex contour. We know what our contour is, right? If this is the complex plane, our contour is something that goes along the branch cut, comes around, and then approaches 0 along the real line. So we've got that contour. And we have an exponential raised to a function, a complex function power, and it's multiplied by a complex function as well. And this seems to come very close, if not identical, to our requirement for this new method that we're going to learn today, the method of steepest descent. And you may remember that that's the diversion we took. We took a diversion just before we even started to study the method of steepest descents. We said, well, do we even meet this basic criteria? Are we looking at a function of a real variable that has an integral representation, where that integral representation is a complex contour of the variable of integration being a complex variable, where we have a function of that complex variable in the integrand multiplied by an exponential of our real variable multiplied by another complex function? And yes, that's what we have. We actually have exactly this expression. And here it is, right? I'm going to put it right there. We have this GZ part is right here, right? The f of z part is right here. I'm including that over 2. And the x is our real variable. It's just popped right up there in the exponential. And z is a complex variable of integration, and that's being called t right here. So all of this is good. We actually have this form, right? This is just some constant mess out in front. And the Hankel function of the second kind is exactly the same situation. It's just a different contour, right? That's the distinction. So we are in pretty good shape right now, except we do have to understand one important caveat. These two functions, f and g, must be analytic. And analytic is a property of a complex function that you just got to understand. I mean, we can't review all of complex analysis. However, we can review a little bit. So let's quickly talk about the analyticity of G and F and then get started on our method of steepest descents. So we're going to focus on the properties of an analytic function that are most important for our steepest descent method. And the first property, it's kind of absurd, but absurd to say it's important because it's actually the defining property, right? The Cauchy-Riemann equations. The analytic functions all satisfy the Cauchy-Riemann equations. And if you take your complex function of a complex variable and you break it down into its real part, so you have now a real function of a complex variable plus its imaginary part, which involves another real function of a complex variable, and then you assert that the complex variable itself has a real and imaginary part, you can end up, of course, with our functions u, x, and y, and v, x, and y, which are real functions of two real variables. And these two functions, in order for our presumed analytic function to be analytic, these two functions must satisfy these Cauchy-Riemann equations. And this is a statement about how the first derivatives of the first partial derivatives with respect to the real and imaginary part of z are related. And now the key about this, and this is an absolutely critical feature of an analytic function, but what makes this so important is this is how you define the idea of having a derivative of f with respect to z. So if you want to understand the derivative of a function, of a complex function with respect to its complex argument, if for that notion of a derivative to even make sense, these relationships must be satisfied. So this problem is worth looking at because we're going to see a version of it when we study steepest descents, right? If this is a point in the complex plane called z0, I want to form the derivative of our function. We have a function on the complex plane called f of z, and if I want to know what is its derivative, the derivative of f of z with respect to z, evaluated at z0, this is just defined the same way as in regular calculus, right? In the sense that it is a limiting process, and this limiting process is what allows us to, well, that is the definition of a derivative. The problem in the complex plane, of course, is when we look at this limiting process right here, and we realize that, wait a minute, z0 plus h, this argument is complex, so h can be complex too. So now, when I look at z0, what is z0 plus h, right? H is supposed to be small, so I could say z0 plus h is right there. I could also say z0 plus h is right there, right? Or it could be over here, right? That could be z0 plus h, right? And in all of these cases, as h gets smaller, what happens is this point comes closer to z0 from three different directions. And once you realize that, you come to understand that this limit as h goes to 0 is really undefined, because the limit itself specifies that h gets small, but it doesn't specify which particular contour this limit is occurring on, right? It could be occurring on this contour, or any other contour. So that is that's a blow. It's a huge blow to the idea of having a well-defined derivative. What you now need is something like a contour integral, right? The contour integral of f of z dz clearly depends on the contour, right? And for arbitrarily different contours, this integral is clearly different. So if you specify the contour, then it's very, very well defined. Likewise, with this derivative, if you specify the path that h takes, now any function can have a derivative. But we want this derivative to be true, to be meaningful, independent of path, right? So the path doesn't matter. And the only way for that to be the case, the only way for this derivative to actually exist uniquely, regardless of what path is chosen to execute this limiting process, in order for that to be the case, the Cauchy-Riemann equations must be satisfied. So you can go through the proof in any elementary complex analysis textbook, and it's totally worth doing. It's the most important principle of defining an analytic function. Now, whenever I study some elementary thing that I've forgotten, like the Cauchy-Riemann equations, I'm going back and reviewing them. I try to deepen my understanding somehow. And in this particular case, I have chosen an approach to the Cauchy-Riemann equations that I never studied when I was learning this material, so I thought I would just break it out here because it really is very interesting. But if we take our analytic function, f of z, and now, by the way, we know what an analytic function is, right? It satisfies the Cauchy-Riemann equations. If you have something that satisfies the Cauchy-Riemann equations, go ahead and call it analytic. Its derivative exists, right? So now imagine we take a derivative of our analytic function with respect to x. Remember, x is just the real part of z, right? And that's kind of like going over here and specifying a path, right? If I'm now saying that I'm taking the derivative where h just equals x, right? As opposed to h equaling, say, iy, where I would be taking the derivative along this path, along this the imaginary path. But if I take the derivative of f with respect to x, I get du dx plus I dv dx. If we satisfy the Cauchy-Riemann equations, look, du dx equals dv dy. So I can replace du dx, right? I can replace it with dv dy. I can place dv dx with du dy and a minus sign, right? And then after a little algebra, well, not even a little, just a trivial move, I pull out a minus I, and I get du dy plus I dv dy, which is minus I times df dy. So I think that's kind of cool. So the point of this is that in order to get these steps to go through, the Cauchy-Riemann equations must be true. So this is a sort of one-step way of writing the Cauchy-Riemann equations. df dy df dx minus I, right? So that's kind of cool. So I hadn't used that form before, but it's very useful. And there's another really important thing that is a QED prerequisite this is something you really do need to understand, that this is a perfect time to introduce this concept right here while we're talking about the Cauchy-Riemann equations and differentiability of f of z, right? So, and it goes like this. If the argument is z, and I know I can write it as x plus iy, just as I have done, I know that the conjugate of z is x minus iy. Now, the first thing I want you to see is that taking the conjugate of something is a pretty sophisticated trick, because what you're doing is you're reaching into the algebraic structure of z, and you're just changing this sign, right? And this conjugation process is actually like going in there and messing with the guts of this function, right? And ultimately, that's exactly what an analytic function is not allowed to do. But I want to demonstrate that. I want to show that an analytic function is never a function of z conjugate, even though it's a function of z. And to me, I wrestled with this for a long time. It seemed to me that if f is a function of z, well, certainly it's also some function of z bar, right? I mean, I guess naively, f is certainly a function of z bar bar, right? Because z bar bar equals z, right? So it just seemed to me that an analytic, a function of z is a function of z bar, because look, the z and z bar are just so tightly related. Turns out that's just not the case. Z, and this is the important point, z and z bar can be treated as independent variables. Just like x is independent of y, in fact, you can broker the fact that x is independent of y to show that z is actually independent of z bar. And the way we're going to do this is we're going to write down x as a function of z and z bar, and y, I guess I'll do it this way, y is a function of z and z bar, and these are the expressions for them. So a partial derivative with respect to x is going to be a partial derivative with respect to z, the partial derivative of z with respect to x times the partial derivative of z, and the partial derivative of z bar with respect to x times the partial derivative of z bar. That's just the chain rule, kind of working the chain rule here, understanding how how z plus z bar can be substituted for x. And so ultimately I can write the partial derivative with respect to x is 1/2 times the partial derivative with respect to z plus the partial derivative with respect to z bar. And I can do the same analysis with the partial derivative with respect to y. Just apply the chain rule, do a little algebra. I get this 1 over y part, but 1 over I, not y, 1 over I times the partial derivative with respect to y. This is these are differential operators now, right? This is the differential operator with respect to x, differential operator with respect to I, written in terms of differential operators with respect to z bar and z. And so I get these two expressions. I get this expression here and this expression here. And by algebraically manipulating these two expressions, I can combine them to get these two expressions for the differential operator with respect to z and the differential operator with respect to z bar. Notice it's kind of interesting. The differential operator with respect to z has the minus sign, and the one with the z bar has the plus sign in it. So it's kind of a little bit backwards. But the point is this now defines these differential operators. If I have a function, right? If I have a function of z, right? And z and x and y and u and v are all defined as we've done it. I've now created these differential operators. So now what I want to do is I want to look at my analytic function, right? F of z. So let's take the partial derivative of f of z with respect to z bar. And if f of z depends on z bar in any way, this is not going to be 0, right? So I now have a differential operator for z bar. It's df dx plus I df dy. And I can execute this because I know that f of z equals u of xy plus iv of xy, right? So I changed my notation a little bit, and u with the little x is the first partial derivative of u with respect to x. And so df dx is u sub x plus I v sub x. Df dy is I u sub y plus I squared v sub y. And then I apply my Cauchy-Riemann conditions. Remember, I'm assuming for a moment that f of z is analytic. I'm assuming that f of z is analytic. So applying the Cauchy-Riemann conditions, I know that v with respect to x, is minus u with respect to y, and v with respect to y is u with respect to x. This minus sign is introduced because there's a minus sign here in the Cauchy-Riemann conditions. Right? But I just did this where I'm replacing this with, this is now u of little x equals v little y, u little y equals minus v little x. So it's a notational change. I love notation, and that's a good change. And it's used a lot, so it's worth getting used to. So now, if I have my Cauchy-Riemann conditions, what we immediately see is that I can substitute minus uy right there, and I can substitute u of x right there, and then I get u of x plus negative, because I squared u of x, and that goes to 0, right? And this becomes minus iu of y, and there's an iu of y, and those go to 0. So this whole thing equals 0. So if f is analytic, and we use this is where we use that fact, right? Analytic means it satisfies the Cauchy-Riemann equations. So if f is analytic and f is a function of z, f is not a function of z bar, right? That is just, I don't know, that blows my mind, but it still blows my mind. So z and z bar are actually independent functions if f is analytic, right? So, and what that basically means is that whenever we look at f of z, when we unpack it, we're never going to see that f of z is a bunch of stuff times, say, the real part of z plus maybe a bunch of stuff times the imaginary part of z. You'll never see an analytic function breaking inside its guts using the real or imaginary parts. And you'll never see it reference z bar as well, right? You won't see it do that. So that's really what's going on there. Is that's sort of part of what being an analytic function is you're not tearing apart the guts of your independent complex variable, and you're not breaking it into pieces. And this is the proof of that. And I knew this was true, but it's been a long time. I may have seen this proof before, but I really enjoyed looking at it this time. So anyway, that's the first thing about analytic functions that we need to know, is that they satisfy the Cauchy-Riemann equations. And that's kind of absurd because that is the defining property of the analytic functions. And this allows us to take derivatives. That's really the big story here, is now we can take derivatives. And therefore, because of this, another key property of an analytic function is that it has a Taylor series about a point where it's analytic. But we'll get to that in a moment. So let's look at another property of Cauchy-Riemann, of analytic functions that we're going to need to understand the method of steepest descents. All right, so the other important property of our analytic function that we need to know for our steepest descent process is that f of z, the magnitude of f of z, has no local maximums. And this is really important because it's going to help us understand how to find these special points that will allow us to do our asymptotic expansions. Now, to demonstrate this, we have to lean on a very critical property of analytic functions. And that property is I should call it a property of analytic functions. It's a theorem of analytic function theory, I guess. And it's the Cauchy Integral Theorem. And it's definitely one of those theorems that you have to learn and you have to know how to recognize and when it's used. It'll be used frequently in physics books and physics demonstrations and analyses. So this is definitely a thing that you have to learn from complex analysis. It's a very, very fundamental principle. And what the principle says, as a reminder for those, hopefully this is not the first time you've seen it, because this is going to be just a quick review of the idea. But if we're located at a point z0 in the complex plane, the value of an analytic function at z0 can be calculated in a very sort of what looks to be like a very bizarre way. Instead of actually just going to the point and crunching the number and getting f of 0, you can also, if you wish, you can orbit the point with a contour, any contour, and you can calculate the value of f of z over z minus z0 along this contour. So this is now the integrand. And it's a closed contour. It's got to be a closed contour. And if you complete that integral, you've got something that's 2 pi I times larger than your function. So you divide by 2 pi I. And that's going to be true for all regions as long as our function is analytic everywhere that's relevant, on the contour, inside the contour in particular. And it's true for any contour, right? So I drew an arbitrary one here, but the one we're very interested in is the perfect circle around z0. And the reason is because we can integrate that very, very cleanly. And through that, we can prove our maximum modulus theorem. So to prove this is called the maximum modulus theorem. And to prove it, you have to assume Cauchy's integral theorem. Well, one way to prove it. And assuming Cauchy's integral theorem is just something that drops down from complex analysis. So I remind you that this is true. And now I'm going to use this fact to show that f of z has no local maximum, which is important to us, or the modulus of f of z has no local maximum. And that's important to us because our method of asymptotic analysis depends on this. Okay, so now what we'll do is we're getting rid of this arbitrary contour, and we're going to, whatever arbitrary contour we have, we're going to deform it to a perfect circle around z0. So the value of z in this integral, because it's on this perfect contour, is always going to be, z is always going to equal z0 plus some little r, which is the radius of this contour, of this circle that's going around z0, times e to the I theta, right? And, this is the polar form. This is a little chunk of complex value. We would have called this h if we were taking a derivative, for example, but it's complex. And it's the polar form of this complex number. So I'm presuming that you understand about polar forms of complex numbers. Of course, we did that a little bit before with some of our other work. And just as a reminder, since we're looking at it and I'm trying to catch up on all of these things, this is always understood as cosine theta plus I sine theta. That's a way you can always think of this. So this thing has a little bit of a real part and a little bit of a complex part. But once we've decided that, once we write this down, we're forcing z to go in the circle because now our variable is theta. This is a constant. Little r is a constant, even though typically little r is not used as a constant for, say, spherical coordinates. In this case, we mean little r is a constant. And finite, right? It's finite too. It doesn't have to be infinitesimal. Because remember, any orbiting contour will work. And e to the I theta, that's what chooses sort of the real and complex. That's what partitions this little piece of complex number into real and complex parts. Okay, so we're going to take this and substitute it directly into Cauchy's integral formula, and you'll see immediately why we chose this form. So let's do that. And here we have it, right? We're substituting this material right here for z, and that gives us this part. And we substitute it for z right there, and that gives us this part. And dz is easy to calculate because that's a constant. And so you pull down an I, and that dz gives you this part right there. So that wasn't very difficult, right? And the beauty is, of course, this stuff cancels like crazy, right? You lose this z cancels with that z. The z zeros cancel, so you're left with just r I theta in the denominator. But that r I theta cancels with this r e to the I theta. So that cancels. So this cancels with. So the z zeros cancel. The r e to the I thetas cancel. The i's even cancel. So when you're done with all the cancellations, this is just 1 over 2 pi times the integral from 0 to 2 pi, because theta going from 0 to 2 pi, this contour integration, which was indicated as any closed contour. This is an arbitrary closed contour. Now all of a sudden it's very clean. It's 0 to 2 pi. D theta. Where'd my theta go? Why do I have trouble with my theta? And so now we have a literal circle. We've turned it into a real integral, is I guess what I'm trying to get at. Or the variable of integration is now real. So anyway, this ends up being just f of z0 plus r e to the I theta. That can't cancel. D theta, right? And that's the value of f of z0. Now notice that's only true for this very specific, this integral here is only true for this very specific circular contour, right? Which is why we chose it. Okay, so knowing that that's the case for this particular contour, now we're going to prove our maximum modulus theorem. So first thing we'll do is we'll take the modulus of both sides, right? I'm going to take the modulus of this and the modulus of this. Now, the modulus of the right side can be greatly compressed into just the modulus of f of z0, right? And now I can take this 2 pi and move it over here. And also, well, first thing I'll do is I'll move it just like that. And then I'm going to convert this 2 pi into the integral from 0 to 2 pi of d theta, right? So if you agree that this integral equals the number 2 pi, you'll have no trouble with that. And now f of z is a constant, so you can consider this guy to be inside the integral. Sometimes textbooks, when they do integrals of various types, they put the measure of the integral on the far left. I always like it over here, and that's probably mostly because that's how my original calculus text did things when I was a student, so I guess that's what I'm used to. But it also tells me everything that's the integrand, right? You could argue that this is this integral times this constant. But the point is that this being a constant, it doesn't matter how you look at it. But we're going to look at it as though it's inside the integrand. So I guess in my preference, it would look like this, right? So this statement here is 100% true. And now we will subtract this side from this side. And what will we get? And here I've just written it out. Actually, what I did is I subtracted this side from this side. Regardless, I get 0 equals this integral. And so this is the integral we want to prove this. Now, this is totally true if we understand that f is analytic, right? And the Cauchy's integral theorem applies, which it does if f is analytic. So this theorem here, this thing is true, right? And we haven't talked about f at all. So this is true in really, really broad generality. So now, the Cauchy integral theorem. Well, okay, so the Cauchy integral theorem says the magnitude, I'm sorry, not the Cauchy integral theorem, the maximum modulus theorem says the magnitude of f of z has no local maximum. All right, prove it. Well, now you look at this integral and say, okay, well, imagine f of z does have a local maximum, and imagine that that local maximum is right here at z0. Say that's it. Say that's where the local maximum is. Well, what does it mean to be a local maximum? Well, it means that it's the magnitude, the modulus of f of z0 is larger than the modulus at any other point nearby. So you make your circle around your point of maximum modulus. And this integral will be true on that circle. But here's the thing. F of z is larger, the modulus of f of z is larger than the modulus of any other nearby point, which is certainly all the points on this circle, right? So this number here is always larger than this number here by assumption, if you assume that this is the location of this maximum modulus, local maximum modulus. So this number here has to be positive. And there's nothing about this integral that's going to change that fact. This is a constant, right? And it's a number. And this is another number that's always smaller. So this measure, this number times the measure will always be positive. And ergo, it can never be 0, right? So the only way for this to be 0 is if this part of the function here always equaled f of z, in which case the modulus at f of z0 is not in fact a maximum or a local maximum. The whole function is constant in that case along this thing. That could happen. If f of z was the constant function, then this condition, this whole condition here would be satisfied. But our assumption is not that it's not a constant function. This is a genuine local maximum. But that contradicts, so Cauchy's integral theorem essentially drives a contradiction with our assumption that the modulus at f of z0 could possibly be a maximum. Ergo, the modulus of an analytic function can never take on a local maximum value. Now, along with that, we can also do a minimum modulus theorem, right? We can say that, likewise, you can't have a minimum modulus, because imagine that if f of z, I guess I'll just point, if the modulus of f of z took a local minimum, then I define a new function, g of z equals 1 over f of z, and that local minimum suddenly becomes a local maximum. With the one exception, if the magnitude of f of z0, which is supposedly a local minimum, say that equaled 0, well, if it equals 0, then I cannot create a gz, right? Gz now becomes infinity at this point where f of z equals 0. And if that's the case, this local minimum must have a value of 0, right? So that's why we pretty much call it the maximum modulus theorem, because you do have this possibility of a minimum equaling 0, but it must be 0, right? It can't be just some local minimum floating out there. It either goes all the way to 0 or not, because if it doesn't go to 0, you can then create a function that does have a maximum, which we proved is not allowed. So it's kind of interesting. And again, this is all about analytic functions. So there are certain behaviors that analytic functions are simply constrained to obey. And this maximum modulus principle is the important one we need to know. All right, and the third and last property of analytic functions that we need to deal with to understand our least descent analysis is that the gradient of u dotted into the gradient of v equals 0. And we need to understand this in terms of u, and u is the real part of our analytic function f, and v is the imaginary part of our analytic function f. But u and v themselves are both real functions of two variables, x and y. And this gradient is this regular gradient operator, as though u is just a regular function of two variables, x and y. So the way to look at this is this dot product is going to be the dot product of del u del x, x hat, the unit vector in the x hat direction, du dy, y hat, right? That's what the gradient of u is. It's defined this way. U's got to be a function of two variables. In this case, it's a function of x and y. That's how we break things down here. And so it has a gradient, and this is the gradient. And likewise for v, dv, partial v with x, x hat, partial v with y, y hat. And this dot product is totally trivial. It's going to be the product of du dx, dv dx, du dy, and dv dy. And it's going to be just a real number or a real valued function. And here it is, right? This dot product of these two gradients. Remember, of course, it goes without saying, I hope, that the gradient of a function is a vector. And so therefore you have this regular old dot product between two vectors, right? And so when you multiply this out, when you execute this dot product, you get du dx, dv dx plus du dy, dv dy. And now remember that the way u and v were derived, it was derived from a function f, which was a complex function of a complex variable that we assumed to be analytic. And by assuming it to be analytic, I can now replace dv dx with du dy with that minus sign, and dv dy I can replace straight up with du dx. And that replacement, when you add all these things together, gives you 0, right? And so therefore the dot product between the two gradients equals 0. And why is that important? So it's absolutely critical for our analysis of steepest descents, because we think about a point in the complex plane, and we imagine a line going through the point that is tangent to the gradient at the point of, say, u. Say it's the gradient of u. And we'll draw that line like this, right? So this is going off in the direction of grad u. Well, if the dot product between grad u and grad v equals 0, that means that grad v must be perpendicular to this. And so grad v must go off like this, grad v. But what's most important is we know that the gradient of v is always perpendicular to its contours. So that means the contour of v, meaning line of equal v, is actually in the same direction as the gradient of u, right? So the line of equal v, remember, f of z is u plus iv. And we're dealing with a function e to the x f of z. So that's e to the x u times e to the x iv. Now, if we are looking for a location of stationary phase, we want a place where this function v doesn't change, right? Because we're dealing with, remember, u and v are both functions of z, right? So we need a path along z in the z complex plane where v does not change. And that path is always going to be, I mean, there's always such a path, right? There's always a path you can take that is a contour of v. But what's amazing and what's so important about this fact here, this gradient dot gradient equals 0 fact, is that if I follow one of these contours of constant v, I'm automatically going in the direction of gradient u. So the very contour where v is stationary, u has maximal gradient. And that's really important because remember, this is getting this guy to not change is stationary phase, right? Getting this guy to be really large for large x, that is Laplace. And putting them both together is going to give us the method of steepest descent. But this is actually the core of the method right here. Understanding that if I follow a path through any given point such that v doesn't change, meaning a path that satisfies our stationary phase requirement, then I'm automatically going in a path of maximum steepest descent. And that now allows us, between all of these features, all of these facts, we're now in a position to study the method of stationary phase and get our asymptotic value. All right, so now we're ready to try to understand our saddle point technique. And what we'll try to do is explain the saddle point technique, and then in the next lecture, we'll actually execute it on the Hankel function. So we know that f of z is analytic. And because of this, we know that we can write this exponential as e to the x times, or x times u plus iv. And our idea is ultimately x is going to be large, right? Because we're looking for this asymptotic form. So we know we need two things for this to work. We know we need to find a stationary contour, that this contour has to go through or has to follow a path that keeps IV constant. But that's not quite good enough because that path also has to pick out a maximal value of u. And the only place where this actually could happen is on a saddle point of the function f, right? So when we talk about our saddle point, we're attacking the function f, and this would be, for example, the graph of the magnitude of f of z, right? So it's not this, we're not looking at this whole thing, we're just looking at this part of it. And the idea is that I can find a path through any point where IV is stationary, right? You know, if I have a contour, if this is my contour C and it starts here and it ends here and it goes through this point, and I want to go through that point in a way where the phase is stationary at my part of the path that goes through that point, well, I just find whatever contour of V goes through that point. Say this is a contour of V in the complex plane, meaning the value of V is constant along that plane or along that line. Maybe I have a whole variety of contours, but that's just one of the contours, right? It goes through this point. Well, what I'll do is I'll just manipulate my path. So I do this, go through the point, and then come back, right? And that's fine because I'm not, as long as that I'm deforming the contour that I'm integrating over, but I'm accomplishing what I want, which means I'm going through this point with a stationary phase. Now, there's still no stationary phase out here, and there's still no stationary phase out here, so that's all going to kill the integral. But there is stationary phase right here, and it doesn't affect the value of my integral because I haven't deformed the contour in a way that is forbidden. The problem, though, is that stationary phase is only half the battle. I need to find a point of maximal u as well. And so the idea then is if I go through, if for some reason I was able to have this point, this saddle point that's indicated on this picture. I took this picture right off of Wikipedia, by the way. If I was able to have this saddle point on my contour, I could arrange to go through the saddle point along a path of constant phase, right? So say my contour goes through that saddle point along a path of constant phase. Then by the properties that we've already learned about, I know that I'm following the steepest gradient of the function as well for u, right? In other words, when I have del u dot del v equals 0, that meant if I was following a path of actually constant v, then I must be heading in a direction of maximal gradient for u. So that's the steepest descent part, right? The problem, of course, is that I might be on a path like this at a saddle point, right? So I have to make very sure that I choose the right direction through the saddle point. In other words, both of these lines could be contours for V in principle. I just have to make absolutely sure that whichever one I follow, U is getting smaller, bigger, and then smaller again. But remember, if V is constant on this little piece of the path, I know that V is not contributing to any changes in the magnitude of F. So all of the changes in the magnitude of F are from changes in U, which is why I know that this bump here is representative of a maximum value for U. So the point being that my contour, if I can drag that contour through a saddle point in such a way that I'm at a constant value of phase, I know that I am peaking through a peak value of U. But it would only happen at a saddle point. So my game plan now is to maneuver the contour so it goes through a saddle point in exactly the fashion I just described. And we know because U is peaking that if X is large enough, then only values of U around the saddle point will matter as long as the phase is stationary. But I'm choosing a path that will force this phase to be stationary. And this can only be done together at a saddle point. So the trick now is to ask the question, can you maneuver the contour through a saddle point? But of course, as I've already shown you, here we've just maneuvered a contour a little bit, but if the saddle point is over here somewhere, let me draw another saddle point. Say the saddle point's over there, I can just maneuver the contour. Let me see, I better do a different color. Hold on. I can maneuver the contour, I'm doing blue. I can say, well, we'll just do this. And I go through the contour in the right direction and go back up here. And if that is a saddle point, and I do this correctly, I'm going through the saddle point at stationary phase, and u is maximal there and nowhere else. It turns out the entire integral is dependent on this very local area right around the saddle point, as long as x is large, right? And we need that large x to make sure that we can sufficiently peak this integral right around the saddle point itself. And all the contributions to this integral are 0 everywhere. So basically what I'm doing is I'm taking a contour that I don't know how to do, and I'm putting it in a way where all of its values accumulated in one spot that I can actually solve for. And that's the intent here. And so we can actually walk this mathematics straight through and come up with what amounts to a formula to understand this saddle point method, or the method of steepest descent. So I hope you understand now why it's called the same thing. The method of steepest descent applies to this point as long as you're on a contour of V. You're always going to be on a steepest descent route through U. And then the saddle point is chosen to make sure that the steepest descent route through U is actually departing a maximum, right? Which allows us to apply Laplace's technique. Okay, so let's drive the numbers or the symbols to get a formula for this method of steepest descents. All right, so to take advantage of all of this, we're going to go to that saddle point. And at that saddle point, we know that f prime of z equals 0, right? That's what a saddle point is. We know that if we find points where f prime of z equals 0, we're not dealing with local maximum, because we know no local maximums are possible for analytic functions. So we are going to take our analytic function and write it as a Taylor series about that saddle point. And there's nothing wrong with the saddle point that would prevent this. And we get this very clean Taylor series that's missing this f prime term. Then we insert that Taylor series. We ignore the higher order terms, and we insert this Taylor series right into our integral representation. And this first piece is a constant, so we'll just pull that part right out, right? And the rest of it is truncated, so we just take out this f double prime term, and we leave that behind. Now, of course, the point is we're going to try to turn this part into a Gaussian. And ultimately, since we're dealing with the saddle point, and we've designed this in such a way that we're going to force all the value right around the saddle point, we replace g, which is g of z. Its only significant value is going to be the value in the vicinity of the saddle point, if we take f large enough. Because we know that the real part of this is going to hit a maximum. So now we're left with this thing here. And what we're going to do is we're going to make some standard substitutions that we have to be familiar with. This should be a minus sign, by the way. I don't know why. We're going to say that z minus zs is r e to the I theta. This is the same thing as saying z equals the saddle point's position plus r e to the I theta. So it's the same substitution we did not too long ago. But z minus zs is r e to the I theta. So this substitution here is going to go right there. And the second thing we're going to work with is, going to be this second derivative. Remember, this is a complex function still. The second derivative is complex. So we're going to write it in polar form, right? It's got some angular part and some magnitude. And we're going to put that together in polar form, and we're going to make that substitution right here. And after those two substitutions are made, we end up with an integral that looks like this. We've made the direct substitution right here, which gives us this part. And the z minus zs squared, that's just r squared e to the I2 theta. That's this piece right here. So that part becomes that part. And dz just becomes e to the I theta dr. Now that part's actually a little bit confusing, because we know that z minus z0 equals r e to the I theta. So we would write dz equals dr e to the I theta, but then we're thinking, well, wait a minute, what about this theta? That's a variable too, right? Don't I need a d theta part? But the answer to that is that we are going through our point. We are going to go through our saddle point. If this is our saddle point, we're going to go through it in a straight line, right? Now, it's not going to last very long necessarily, but the value of theta along this straight line is going to be a constant. So the only thing that's really changing is, remember, this is z0, and this piece here is re to the I theta. But if theta never changes, that means we are going through z0 as a constant. Now, of course, when we get through the other side of z0, things obviously change a little bit on the other side, but the point is that theta is not a variable that defines the contour and is changing. The part that we care about is just dr. So we're going to leave this as e to the I theta dr. But we still have to pick theta. So now look right here. We have e to the I 2 theta and we have e to the I beta. So we're going to put those together and we get beta plus 2 theta. Now that's still phase, right? And we still are going down this contour. Nothing here is enforced stationary phase yet. All we know is we're doing this around the saddle point. We still haven't chosen this direction of integration across the saddle point yet. Choosing theta is equivalent to choosing the direction through the saddle point that we are integrating. So we want to choose theta so that beta plus 2 theta equals pi, right? And then this becomes e to the I pi, which is -1, and that is a real number, right? So we turn this into something that's real. And if we choose that theta, then we certainly eliminate the oscillations. So the path through z0, the way we enforce these this elimination of oscillations is by getting this exponential to be, we want the complex part of this exponential to go away or to be constant. And to make it go away is to get this part to be entirely real. Because remember, that's real, x is real, 2 is real, r squared is real. So everything that's complex lives in here. So if I can turn this into something that's real, I'm good. So I choose theta such that beta plus 2 theta equals pi, right? I'm going to make that choice. And then that e to the I pi, this part right here, this part right here just becomes that negative sign down there, becomes this minus sign. And this integrand is now entirely real, right? And this e to the I theta just pulls outside the integral because we're only integrating on dr. So now I've got a Gaussian here, right? That's a Gaussian. And that's of the form, right? That's of the form the form e to the minus, let's see, e to the minus alpha r squared, right? Because everything in here is going to be real, right? And x is going to ultimately be large in our problem, so it's going to be positive. So this fits that form. So now this integral, because we're stationary, and we're going through we're going through our saddle point. Where did I plot that saddle point? We're going through a saddle point with constant phase. We now know that we're dealing with a peaked out value of u. So now going to Laplace's method, I know that if I pick x large enough, then I know that this sharp peaking is just going to pick out the one value of gz, right? That is the value of g at the saddle point. And I can also begin to execute this integral. And dr even though I'm only doing it right around z0, right, in a very narrow area of d0, am I integrating with this straight path, right? Because remember, I have this whole contour I have to make happen, right? But I now know, because I've designed it in this way, I now know that the contribution pretty much everywhere else is not going to matter. It's not going to matter. That's the sort of the black art of this asymptotic stuff. And so I can now take this contour and just turn it to minus infinity to infinity of this thing, and then just go ahead and execute it. And this ends up being the formula, right? With this idea that theta is pi minus beta over 2, right? To satisfy beta plus 2 theta equals pi, to get this guy to be -1. So it's pretty impressive that you land with a formula, right? If I know my, if I know, let's see, if I know this integral representation, right? I know this integral representation right here. I know G, I know F. This thing down here is virtually a plug-and-play formula. I do need to figure out where the saddle points are, right? So I figure out where the saddle points are, calculate G there, figure out where the saddle point is, calculate F there, and then I create this function, this thing. This is just going to be a number, and I create this function. This is just going to be e to the x times a number. This is already fixed by my choice of by our choice beta, which is the path through. No. Beta was the phase of the second derivative, right? The phase of the second derivative. So I calculate theta, and theta is just a function of beta. In fact, I don't even need theta for this thing, do I? Where does theta show up down here? Hold on. Oh, right. I used this formula for theta to substitute that into this, right? So theta shows up through indirectly, but it's there. And then I just have to calculate this guy. Notice x shows up in the denominator to the 1/2 power, which we can almost guess is going to help us with our Hankel function. But this formula is not that tough to apply. There is a subtlety to it. First of all, the saddle point may not be a clean saddle point. It may have 2 or 3 different pieces to the saddle. You can have some weird saddle points out there. And also, it is possible that there will be 2 directions that satisfy theta. This may not be unique. In fact, it's not unique. So you have to make sure you pick the right one. You have to make sure you pick the one with the contour where the real part of the function u is actually decreasing, right? You need to find it where u is getting bigger and then smaller, not smaller and then bigger. In other words, we've got to make sure that we're following a contour that when you calculate the modulus, you're actually peaking u. Because remember, the v is not going to contribute to this modulus, because v, we're specifically choosing a path through this point where v is constant. So the only way this modulus can change is with u. So u has to be getting bigger and smaller as long as we're on a path of constant v. And we know that the path of constant v will be this steepest piece, right, as opposed to, say, something like this, which is a lot smoother, would be a lot more gentle. That would be more gentle in u. It would still peak u, but it's not a constant phase path. Because it's analytic, we're really lucky that the constant phase path is the same as the peakiest path for u. It's just this really clever observation that whoever invented this technique, Kelvin or or Laplace or whoever it was, realized all of these facts. So anyway, we're left with a formula. This formula right here, and next lesson we will apply that formula to our integral representation of the Hankel function. And you can see we're just going to, by rote, apply it step by step by step. We're going to have to do a few expansions, and then we will end up with our final expression for the Hankel function, the ordinary Hankel function, which will convert to the spherical Hankel function. Okay, so I'll see you next time.